This is the first of a pair of lectures on the subject of dimensional analysis, or the nature, qualitative nature of the structure of physical dimensions and the nature of physical laws. In the first lecture, I will attempt to present dimensional analysis as it is classically presented in books on that subject. For example, Sedov's treatise on the subject. And in the second lecture, I will attempt to provide an understanding in qualitative terms where this method comes from. The first lecture is relatively self-contained. The second lecture rests on having heard the lectures on extensive measurement, conjoint measurement, the one on meaningfulness, and the one on non-additive concatenation structures. I will be pulling material from all of those chapters together in giving an account of dimensional analysis. The part of the foundation of measurement that is covered in this first lecture is in Chapter 10, Sections 1 through 5. The second lecture, the material there is partially discussed in Chapter 10, but it is not completely satisfactory there, and we've undertaken to revise it and presented that in the meaningfulness and non-additive concatenation chapters. So it'll be pulled out of that material. Now, the method of dimensional analysis rests heavily on the structure of units of physical measurement. We all know that the units associated with physical measures have the property that they either are unitary measures, for instance, the dimensions of length or of mass are usually taken to be unitary in nature, or they're composite and in the form of products of powers of the units of the basic measures. So, for example, energy has the units of mass times the unit of length squared divided by the unit of time squared. This structure that we're all familiar with exists, however, only because there are physical laws that establish these interconnections. And in fact, it appears that one can classify the laws into three general categories. The first one are laws that relate merely to dimensions, binary laws, and those are ones that establish universal constants, because what in essence they do is establish that two apparently separate dimensions, for instance inertial mass and gravitational mass, are in fact the same dimension, and the values in the two dimensions are related by some constant, in this case the universal gravitational constant. Or in the case of relativity theory, it was discovered that mass and energy were related, with the constant connecting them being the velocity of light. I will not be making any significant use of the binary laws, except to mention that it is important in the method of dimensional analysis to be aware of the role of universal constants, and they sometimes have to be brought into play. The next class of laws are trinary in nature. They involve relating three dimensions, and they're the ones that establish the primitive connections among the units. For instance, a law like Newton's forces mass times acceleration establishes a connection between three separate dimensions, force and mass and acceleration, and does it in the form of a product of powers. In this case, the powers are all first power, and so it's just a simple product. The case of energy, kinetic energy being half mass times velocity squared, is a more typical example of product of powers. And these trinary laws are the ones that have permitted the structure of all the dimensions of physics to be interlocked very tightly with one another. And then there are the other laws of physics that are not of these trinary character and that have a more complicated structure, and it is those that we will then try to understand more fully once we've pieced together the various dimensions. Now, the mathematical structure of these dimensions is often taken to be described as a numerical vector space. This tends to cause a little bit of problem because one needs to be able to distinguish carefully between dimensions and certain operations that will be carried out within a dimension, changes of units in essence. And it's proved to be more satisfactory to axiomatize the notion of the structure of physical quantities in algebraic terms and then simply prove that it has the appropriate vectorial representation. So I'll approach it that way. The axiomatization that I will be using is stated in Chapter 10, and it is due to Hasler-Whitney. We're going to axiomatically treat the set of all the physical quantities that we're going to be dealing with, the huge set. We'll call that A. We're going to have a distinguished subset of it that I call A plus. Intuitively, what A plus are the positive parts of all the dimensions involved. And star, a function that maps A cross A into A, and is a composition among dimensions. The idea is that you have two quantities, two physical quantities that have dimensions, and you can combine them in some fashion under star, is the combining operation, and create a new dimension. And the axioms are an attempt to characterize the nature of that combining. And formally, we'll say that this structure composed of A plus, and star is a structure of physical quantities if the following conditions are met. First of all, the combining operation is assumed to be associative and commutative. You recall that associativity means that if we have A star, B star, C, that is not different from A star B, quantity star C. And commutative simply means A star B is the same as B star A. The order of the dimensions doesn't matter. Secondly, within the space, we're going to have the real numbers, that is, dimensionless quantities. The reals will be interpreted in this context as representing dimensionless quantities, and the intersection of the dimensionless quantities with the positive part of the space leads to the positive real numbers. And in particular, if we have two dimensionless quantities, alpha and beta, then their composition under the star operation is simply multiplication. You're working then within a single dimension, the dimensionless one, and you stay in that dimension under star, and it produces simply the product of the two numbers. One acts like an identity on any element, and 0 acts like a 0. It maps into the dimensionless quantity 0. For any quantity that is distinct from 0, then either it or the inverse that is obtained from it by multiplying it by -1 is a positive quantity. So the set A plus includes either the element or, in essence, the negative of that element. 6, if we have two positive quantities, their composition is also positive. 7, for any non-zero element, there is an inverse element such that the product of those two dimensions is dimensionless. So we can for any dimension, we have the inverse of that dimension. For example, if you have mass, then you have the inverse of mass as a dimension in the structure. And finally, if n is an integer and x is a positive element in the structure, the assertion is there's a unique element, also positive, such that the nth power of that element is equal to the given element. So that, in essence, we're able to take roots, where by nth power I mean y star n times. And this assertion is that we are able to take roots, and we in fact write it in the usual way, that y is the nth root of x. Now, an example of such a structure, just to be fairly concrete about a numerical example that satisfies it, is suppose A consists of the real numbers composed with m copies of the rational numbers. So a typical element will be a real followed by a sequence of m rational numbers. And define star in the following way. You multiply together the two real numbers. That coincides really with this property here, that you're going to require the reals in the system to work, the starring operation will work multiplicatively. And then we'll add the rational numbers pairwise. So you add row 1 to row 1 prime, row 2 to row 2 prime, row n to row m prime, to produce a new element in the system. I'll come back to the rest of this in a minute. That structure can easily be shown to satisfy these axioms, and in fact is a fairly typical version of it. Now, one wants to go from this structure to something that really is talking about the dimensions per se. Here we're talking about physical quantities, and we've axiomatized it with the idea of dimensions involved. And what I want to do next is to pull out the dimensional structure itself. So I'll define the dimension of the element A. The element A is a particular physical quantity. Its dimension is all of the things that you can obtain from A by composing it with real numbers, alpha star A. And I'll refer to that as the dimension involving A. The set of all such dimensions I'll call bracket capital A. And I'll define a composition, and I'm going to use the same symbol. It's got a double meaning, but I think we can keep it straight. The composition of two dimensions is the dimension of the composed components. Now, as usual in working with equivalence classes, which these are, you must prove that this operation is well defined, that if I choose another element, A prime, that's in the first dimension, and B prime in the second dimension, that I will indeed get the same dimension here, and that's easily verified. We also can define what we mean by a power of a dimension, at least a power to a rational power. We're not going to have irrational powers. They could be introduced if one wanted to. However, in all of the examples from physics that I'm aware of, rational powers suffice. One does not hear of a dimension of a physical quantity that has an irrational power involved. and that is simply defined as the dimension of the object to where you first compute the jth root. If it's the rational number I over j, you compute the jth root of the object and then take the ith power of it and then get the dimension of it. And again, one must prove it's well defined, which is not terribly difficult. From this reduction to dimensions, you're able then to establish the following theorem, that if you begin with a structure of physical quantities and you introduce the notion of dimensions as just done with the exponent operator and the star operator, one can show that this is a multiplicative vector space over the rationals, with the identity being the real numbers, the dimension of the single number 1, and with the inverses defined in terms of the dimension of the inverse element that's postulated to exist in axiom 7. So that puts it into the vector space framework, which is the one that is usually introduced right off in the typical textbook on dimensional analysis. However, I think it's useful to keep quite separate, as we have done here, the role of the individual quantities and the dimension that they're a member of, which comes here. And it's these dimensions then that get characterized as the vector space. Now, once you are thinking in terms of a vector space, it's immediately suggested that one might consider the case of a finite dimensional vector space, which can be characterized in the following way. I'll call a set of dimensions denoted the dimension of A1 through AN. I'll call it a base of the vector space if it has two properties. First, that it spans the vector space in the following sense, that for any other dimension there exists rationals rho 1 through rho n such that that dimension can be represented as the first base raised to the rho 1 power composed with the second one to the rho 2 power and so on to the nth one to the rho n power. And I will say, or put back into the original space of physical quantities, it's saying that the element A can be represented as a a real number composed with the element, the typical element A1 of the first base dimension raised to the rho 1 power composed with the second one to the rho 2 power and so on. That's what I mean by spanning the vector space. I will say the base is independent if the equation that some set of powers of the base dimensions composed to be dimensionless, to be really this is the dimension of 1, the vector space. If that implies that all of the exponents have to be 0, then we'll say the base is independent. It means that no one base can be written as products of powers of all the remaining ones. And then we say the vector space is finite dimensional if and only if it has such a finite basis. If I go back to my example, this is a finite dimensional case. What we have here, for instance, is first the dimensionless quantities, which involve putting all of the rationals equal to 0 and just having the real in the first component. A typical dimension, then, is to have a fixed set of rationals, rho 1, rho 2 through rho n. Those are fixed, and we permit tau to vary over all possible values. That would form one of the dimensions, the dimension that is characterized by those exponents. And the basis for this structure would be the set of all things that are obtained with the particular choice of all of the rows equal to 0, save the one in the ith coordinate, which is equal to 1. And that forms the basis of this vector space, as is fairly easily demonstrated. Now, within this structure, physicists have been much concerned with particular transformations. The intuitive idea of the transformations is that all of the scales that the physicists are talking about are ratio scales, and one would like to be able to talk about what happens when you change the representation of the ratio scale. That is, you make a change by a multiplicative positive constant. So we've got to characterize within the structure those transformations that correspond to changes of unit in the representation. And that is done in definition 10.2. We'll say that a function phi that maps the space of physical quantities into itself is called a similarity if it meets the following conditions. First of all, it's a function that's one-to-one and onto. Second, it has the property that homomorphisms have, or actually automorphisms in this case, namely that when you apply it to the composition of two physical quantities, it becomes the composition of each of them separately. Thirdly, it takes a dimension into itself. That is, you take a particular physical quantity, you apply the similarity, and then look at the dimension of the resultant. That is the same as the dimension of the physical quantity itself. So this mapping, if I think of the dimensions as, let's say, in a two-dimensional case, a similarity will take a point in this dimension and move it to another point in that dimension, and it'll take a point in this dimension and move it into that dimension. It will not take a point here and move it into that dimension. It stays within the dimensions. Moreover, it takes positive quantities into positive quantities. And finally, in the case of the dimensionless quantities, the real numbers, it does not make any change. It simply takes a real number into itself. And that physicists have interpreted as a representation of changes of units in the structure. That if you were to change the units in a space of physical quantities, that would be represented by a similarity. And indeed, the theorem that one can prove about the nature of similarities is a strong justification for that belief. The theorem states as follows. Suppose that phi is a similarity in a finite dimensional space of physical quantities, structure of physical quantities. Then the assertion is that there are n real numbers, and I'll denote them as phi sub I. Usually phi is to represent a function, and it is indeed a function here, but I want to emphasize that these real numbers are locked into phi, so I'll use the same symbol and a sub I to represent the different numbers that are involved. So these numbers exist, and if we take the base to be the dimension that has of A1 and through the dimension of AN, then the assertion is that phi applied to any of the A sub i's is phi I composed with AI. And secondly, if I take a physical quantity that is written as a real number composed with a base to the various powers, this is a typical element of the structure, given that you have a finite dimensional structure with the base A1 through AN, then the similarity of that element becomes that element multiplied by this real number, which takes the alpha from that representation and then modifies it by the phi1, which characterizes how the first base is changed under the similarity, raised to the exponent that that first base is appearing in, multiplied, and this is now multiplication here, ordinary multiplication, by phi 2 raised to the rho 2 power, and through all of the changes of units to phi n through the rho n power. And that is indeed what you would expect a change of units to look like in the case of a finite basis, that you know what you've done to each of the base elements, and the change is run through the powers that they come to and simply changes the number then involved at the outset. I'm sorry, I've made a mistake here. This alpha does not belong here because that's already included in the A here, so that you're just changing the A by the effect of the units. That was a mistake. Conversely, any function that I construct in this fashion is a similarity. It meets these conditions over here of the definition of a similarity, so that it appears to capture very nicely the idea of change of units. Now, the next thing I want to begin to talk about is the nature of a physical law that can be formulated within the structure of physical quantities. What does one mean by a physical law? Well, first of all, a physical law is a statement involving a certain number of dimensions. These are the dimensions that are relevant to whatever it is we're talking about. If, for instance, I'm as I'll give an example later, talking about the lift on an airfoil, then certain things will be relevant, like the airspeed, the density of the air, the viscosity of the air, and several other things that we'll come to when we get to that example. So that the law entails a listing of dimensions, and in fact I will assume that the dimensions that are relevant are all the positive parts. And I'll call them, in whatever the example is, I'll say there are S of them, and I'll label them just 1 through S, P1, P2 through PS, and those are particular dimensions in the structure. And then the law is usually stated in the following fashion, or something that's equivalent to it. There's the assertion that there is a function that maps from the Cartesian product of the dimensions, the relevant dimensions, into the real numbers, such that what one can observe physically are those combinations of quantities from the several dimensions that satisfy the constraint that the function of those values is equal to 0. So it's a way of characterizing a particular relation on the Cartesian product of these dimensions. It's the, if you will, the locus of points that satisfy this constraint. That is the typical form of a physical law. It's a device for establishing a particular relation, which relations is asserting these are physically realizable combinations. Now, physicists have postulated that the functions, or equivalently the relations, that can appear are those that satisfy a particular constraint known as dimensional invariance. The function f is said to be dimensionally invariant if and only if it has the following property, that f will be 0 at the values x1 through xs, if and only if for every similarity in the structure it also goes to 0 at the value phi of x1 through phi of xn. That is, that you change the units of the structure and you will get a set of values that also produce an acceptable combination, physically acceptable combination in the relation. That is, they'll cause the function f to go to 0. Now, that property of dimensional invariance is argued for roughly in the way I have done it, with an appeal to changes in units. And say, one typically says, well, the nature of the physical law should not rest upon the particular representation that we're using of the physical attributes, and therefore should be invariant under these changes. This is an argument that I've always found partially convincing and at the same time very slippery. So one of the things that I'm going to be interested in doing is trying to provide a rational account of why a physical law should be dimensionally invariant. But before turning to the question of where dimensional invariance is coming from, I want to go on to describe how it is used in this method known as dimensional analysis. So we'll make the assumption, along with the physicists, that any physical law exhibits dimensional invariance. The basis for the method rests on a theorem that was first precisely formulated in 1914 by Buckingham. It had, however, been utilized in various ways during the 19th century by various physicists, including, if I remember correctly, Helmholtz and Fourier. Buckingham formulated it completely precisely, and it is the basis of the method of dimensional analysis. And let me attempt to describe that theorem now. It's presented as Theorem 10.4 in the Foundations of Measurement, and it is proved there. I'll not attempt to prove it here. So we're dealing with the situation where we've got a set of S positive dimensions and a function that is mapping from them into the real numbers that is defining the lawful relation. Let us index those positive dimensions in such a fashion that the first R of them, which actually less than or equal to S, is the maximal number of maximal independent subset of the subspace generated by all the powers the products of powers of these S dimensions. So we look at the subspace that's generated by that set of dimensions, which may be less than the entire space of structure of physical quantities, and we ask what is the minimal subset of these dimensions that will span that subspace. And we denote those by 1 through R. And now, of course, we assume that we have this dimensionally invariant function f, and the assertion of the theorem is that we can represent the function f in a very special way, namely that there is a mapping from S minus R Euclidean real space, so simply the Cartesian product, the reals with itself, S minus R times. That is the number of relevant dimensions that go beyond the basis needed to do this spanning operation. I shouldn't call it basis, but really a selection of these positive dimensions that will span this subspace. So we have a function from that Cartesian product of reals into the reals, and a system of rational numbers, rho sub I j, where j runs over the set of dimensions that spans this subspace, namely 1 through R, and I runs over the remaining ones that aren't in that quote basis for this subspace. And the assertion is in two parts. First of all, that for any x in one of the dimensions not part of the selected maximal independent subset of dimensions, for any x outside that, we can take powers, and I've chosen to write them as negative powers of the rows. That's just a convention of how I write the rows. We can take the given element and then compose it with powers of all the basis elements and end up with a dimensionless quantity. In other words, another way of writing it is that the x sub I is expressible as a number times the... So x sub I is pi I minus r, a real number, composed with x1 to the row I1 and on down to xn row I(n). So that it is expressible in terms of the temporary basis for this subspace in a dimensionless fashion. And secondly, the law that singles out certain relation on these holds if and only if f, capital F, of these dimensionless quantities is equal to 0. So we've replaced the law which was stated in terms of quantities with dimensions in a somewhat simpler relation among the several dimensionless quantities that exist. And conversely, any such function as this, in fact, when then re-expressed back in terms of all of the separate dimensions, it becomes a dimensionally invariant law. So that the essence of this theorem is that if we're willing to deal with dimensionally invariant laws, they have a particularly simple structure, and it is of the following general character: that you pick out a temporary basis for the dimensions that are involved, and then express everything else in terms of that basis, and you can in essence find the coefficients that permit that expression. It's partly in terms of the exponents and partly in terms of a numerical coefficient that describes it, and the law can be replaced by a law stated entirely in terms of those dimensionless quantities. And that is the main device that is then used in dimensional analysis. Typically, one rewrites this law in the following way. If you're lucky and things come out right, you will find that the thing you're interested in, the quantity you're interested in, or the dependent variable in the situation, appears in only one of the dimensionless quantities. And let me, with no loss of generality, assume that it occurs in the last one. And indeed, let me assume that the variable that I'm interested in is the one that is subscripted S. So I can solve this equation for the last component. That is, I can, if things are monotonic in F, I can solve for pi of S minus R as a function of the remaining pi's, 1 through S minus R minus 1. And then in turn, I can write x sub S in terms of, as I indicated over here, if this were x sub S, I'd have the S here and the S here, and S there and there. And so I would write it that way, and then I would replace the pi S minus R. This is S minus R here. I would replace that by this function and get this expression, which would say that my dependent variable had this particular dependence on the first R variables, and then that is modified by the dependence of an unknown function g on these dimensionless quantities. And frequently, reasonably frequently in examples, this either becomes a constant or a very simple function of several important dimensionless quantities, and that in a certain sense one learns the structure of the dependence here subject to some sort of modification by this unknown function. And sometimes one can use empirical techniques, and I'll discuss that in a minute, to estimate this, and that then tells you a great deal about what's going on. The method, when you see it in operation, almost makes you feel that you're getting something for nothing. It's really surprisingly powerful. But let's make it very clear that it is not getting something for nothing, that you really have a great deal of built-in information that's extremely important. What is the information you have built in? First of all, it is the structure of physical quantities that describes all of the interlock among the various dimensions that is encoding in that fashion an enormous amount of physical information, namely all the laws that went into establishing the trinary laws that went into establishing the connections between the several dimensions. So that information is embodied in the structure of units. Secondly, and very important, is the assumption that you know the relevant dimensions of the law in question. Now that requires an enormous amount of knowledge. If it turns out that you're wrong and you list inappropriately the dimensions, the worst case being is that you omit a relevant dimension, you can be very seriously misled by applying this method. The method is valid only to the degree that one in fact knows the variables in question. And that entails a very considerable understanding of the physical process. In fact, in general, I would say that one really wants to have a very well-developed theory of the physical process that you're trying to study before you attempt to use dimensional analysis. It is then usable to substitute in a way for solving the full dynamic equations that are involved in certain special cases and getting the form of an answer without actually going through the solution of equations. But the equations or the physical theory tells you what variables are involved in the situation. And one must be extremely careful on that point. Now let me try to illustrate it with a simple example that's dealt with in the text. And this is the example of an airfoil. I will idealize the airfoil as a very thin plate, rectangular plate. There's the x dimension is in line with the plate. The z dimension is perpendicular to the plate. The y dimension is coming out from the board and perpendicular to the airflow. And I will assume that the plate has length in the y direction, and I'll treat it as a square plate with a certain length in the y direction and a length in the x direction, no thickness, a constant flow of fluid, and the plate is at an angle alpha to the fluid. And you now produce forces perpendicular to the plate and parallel to the plate, which you can decompose into two forces, namely, I haven't drawn this any too accurately. The lift, that is the force going directly up perpendicular to the airflow, and the drag, the force against the airflow. And lift and drag are things obviously of interest to anyone concerned with aerodynamics. And the question is, what is the dependence of these forces on the various physical variables that are involved? Now, the physical variables that I will take into account, and I am going to make some idealizations here, I will certainly take into account the velocity, the two lengths that I mentioned, the density of the fluid, which I'll denote by little d, the viscosity of the fluid, which I'm going to denote by mu. I'll neglect certain things. I've said I'd neglect the thickness. I'll neglect the temperature, except to the extent it has an impact on density. Any electrical effects that might exist, the compressibility of the fluid, will all be neglected. And I'll simply take into account these variables: velocity, the length, the density, the viscosity, and of course the thing I'm interested in, which is the force on the plate. Now, one knows what the dimensions of some of these quantities are. For instance, we know that a velocity has dimensions of a length over a time. I think most of us know that density has the dimensions of a mass over a volume. Viscosity, many of us don't know the dimensions of. However, one can certainly go look it up. For example, there's a table of dimensions at the end of Chapter 10. And you can then set up in tabular form all of the relevant dimensions that are involved and all of the variables. So, for example, the force in the z direction, incidentally, it will separate lengths in the x, y, and z direction. I'm going to treat them as though they were separate dimensions, and I think there is a very good reason to do that. The force in the z direction, then, is a mass times an acceleration. So the mass appears in the first power. The acceleration is, of course, a length in the z direction, the direction of the force, and time appears in the inverse second power. The velocity in the x direction is a length in the x direction, and time in or the inverse of time. Velocity in the z direction is length in the z direction and inverse time. Length in the x direction is length in the x direction. Y direction is that. The density involves the three lengths to get the volume, all inverse, and the mass in direct proportion. And then the one you have to look up is viscosity, which depends on the length in the y direction, the mass, and the inverse of time. Now, there are systematic ways of finding the dimensionless quantities. I won't go through any of the algebra. It's fairly straightforward. But you can verify for yourself that in terms of these variables, there are two dimensionless quantities, which I'll call pi 1 and pi 2. The first one involving the velocity in the z direction, the length in the x direction, the density divided by the viscosity. And the second one involving the thing we're interested in, the force, and the velocity in the z direction squared, the density, the length in the x direction, length in the y direction. So the law is that f of pi 1, pi 2 is equal to 0, or solving for pi 2, we'll get pi 2 is a function of function g of pi 1. And then if I express what pi 2 is, I get the following expression. And now I'll solve the v in the z direction is the given velocity times the sine of the angle of attack, and the lengths I will replace by the actual lengths of the plate in the x and y direction, thereby producing the area of the plate. I'll call that A. And I will rewrite the velocity in this term. I'll break it down into the angle of attack term and call the resulting number, which is velocity times the length typical length, the density divided by the viscosity. That number is known as the Reynolds number. And so what the law is the force in the z direction is proportional to the square of the velocity, the square of the sine of the angle of attack, the density and the area, and that is all modified by something that depends both on the angle of attack and the so-called Reynolds number. Now that's telling us a great deal about the dependence of the force on the various variables involved. And in fact, one can then proceed to the performance of the airfoil in a very simple kind of way, simple in principle. We can estimate for the air that the airfoil will be flying at, the airplane will be flying at a certain altitude. We can compute its density. We have the typical length dimension of the airfoil. We can talk about the velocity that we're expecting to deal with and the viscosity of the air and get an estimate of the Reynolds number for the conditions of the flight. Now, if we can find another fluid that we can use in an air tunnel, a wind tunnel, that has the same Reynolds number, that is, we'd like to make a small model of the aircraft we're dealing with, so we would reduce the L, and we have to compensate for that either by manipulating the density or the viscosity of the fluid we use or the velocity that's used in order to reproduce the same Reynolds number, then one can study the performance of the airfoil, because this quantity you can make to be equal to the value that you're going to deal with in the real world, and these dependencies, of course, are something that you have direct control over. So that it is because of this kind of structure that the whole thing depends on a single number, the Reynolds number, that the possibility of wind tunnel study of aircraft is well, this is the reason that kind of study makes any sense at all. Now, you see that we have really found out a great deal by knowing only really the relevant variables. This is, I think, the impressive thing about the method of dimensional analysis. It has not, I should point out, proved yet to be of very much use in any sciences outside of physics. I can't think of any effective uses of it in psychology, and that arises, I suspect, mainly because there are no truly psychological variables that have been incorporated into the structure, so-called structure of physical quantities. At the present time, I'm unaware of any addition to that structure that lies outside of the classical dimensions of mechanics, thermodynamics, and electromagnetism. There are no inherently biological dimensions that have been adjoined to the existing structure of physical dimensions, and I think it is for that reason that one doesn't really see effective uses of dimensional analysis outside of truly physical variables. For good examples of how this method has been used by physicists and engineers, I warmly recommend Sedov's book on the subject. Now, our problem from the point of view of a measurement theorist is really to do two things. The first is to try and understand, in terms of qualitative structures, where this structure of physical quantities is coming from. It's reasonably clear that many of the individual dimensions are thought to arise as ratio scales from extensive measurement. It's also reasonably clear that some of the product structure that we're dealing with is thought to arise from some sort of conjoint measurement. But then there's a question of how these two kinds of things interlock and why they lead to the particular structure that we've postulated in the notion of a structure of physical quantities. There needs to be something more than simple hand-waving that says, well, we've got extensive measurement theories, and we've got, on the other hand, conjoint measurement theories, and somehow or another they piece together to form this structure. One really needs to spell out what that piecing together entails. And so that will be the first thing we have to take up in the next lecture on dimensional analysis. And then the second question, and one that has clearly perplexed a lot of physicists who have written on the subject of dimensional analysis, and that is the issue of why do you impose the property of dimensional invariance on physical laws. It is certainly key to the method. There's no question that's a crucial concept in Buckingham's pi theorem, and the method entirely rests on the pi theorem being correct. So there's a philosophically interesting question of why is it that physical laws are dimensionally invariant? And that will be the second issue that we take up in the next lecture on dimensional analysis.